In lesson 8.2, we are considering the series, in other words, the sum. This is said to be a sequence of partial sums. The concept is that we are creating a pattern for the sums based on the addition of the terms. So the sum of one term, the sum of two terms, the sum of three terms, and in the S sub n case, it's the sum of n terms. Of course, we want to know what happens as n goes to infinity. And if the pattern for S sub n does converge, it will have a limit, and if it doesn't, it will diverge. A series that we are familiar with would be 20 plus 10 plus 5 plus 5 halves plus 5 fourths. We should recognize that it's geometric. The common ratio is 1/2. The first term, of course, is 20. And this lesson recreates a formula we've had in the past, that the infinite sum of a geometric is the first term, all over 1 minus the common ratio. For this problem, 20 all over 1 minus 1/2. Of course, that turns into 40. So the infinite sum is 40. This is true, this formula, only when the absolute value of r is less than 1. So the ratio itself has to be smaller than 1. Could also be negative, but of course between -1 and 1 then. You're welcome to use that formula whenever you recognize the series as geometric. Geometrics can also be written in a sigma form, and you have to recognize it as geometric. Here's an example. Suppose n goes from 1 to infinity on 2 to the 2n over 3 to the n. You may recognize that 2 to the 2n is 2 to the second to the n, so it's 4 to the n, and the denominator is 3 to the n, and if we recognize that we can write that as 4/3 to the n, the common ratio would be bigger than 1. In fact, it's 4/3, and therefore it would diverge. So we point out that it's geometric. The common ratio is 4/3. And of course that's bigger than 1, and so the series diverges. We are not able to get its sum. Another geometric would be a repeating decimal. 2.317 repeating. As a decimal, it's 2.3171717, and so on. Well, that can be rewritten 2.3 plus 17 over tens, hundreds, thousands, that would be 1,000, and 17 over 1 with 5 zeros, and a 17 over a 1 with 7 zeros, and so on. We can recognize that the infinite repeating part is geometric. First term being 17 over 1,000. The common ratio being 1 over 100. Each time we tack down a couple more zeros, we get 17 over 1,000 divided by 9 99 over 100. And that becomes 17 over 990. When we add the 2.3 onto that, that's 23 tenths. Plus 17 over 990. It gives us 1147 over 495. So repeating decimals are geometric, and the repeating portion can be written as an infinite sum. You can obtain its sum, and I did probably forget the 2.3 on this side. And of course the finite part combined with the infinite part we put together to get the final sum. There is a series that is geometric that we will refer to in the future. 1 plus x squared plus x cubed, and so on. Of course, the pattern is simply x to the n, where n starts at 0 and goes to infinity. It too is geometric. So the first term is 1. The common ratio is x, and it's true that that infinite series is equal to that function. This is something that we will look at in the future when we get near the end of Chapter 8.